Hello everyone, and welcome back to the Kohi Game Engine Series. This is video number 42, and today we are going to talk about free lists. Free lists are something that we've touched on repeatedly that we're going to need for several videos in a row now. And so today we're going to finally get into what a free list is, how it works, and we're going to go into an implementation of a free list. Okay, so before we jump into any of that, I want to really quickly thank the partners of the channel, which is the highest tier of membership, as well as the highest tier on Patreon. So our partners are Eearslya, Wensheng, Caden, Joel, and I hope I'm pronouncing this correctly, Aneudy. Thank you guys so much for your support. It is greatly appreciated. I also want to give a big thanks to all the other folks here that are listed on the screen at the moment. The support from you guys means a lot to me and helps me grow this channel and be able to make investments into the channel. Okay, so what is a free list? So our formal definition here of a free list is a data structure that maintains the locations and sizes of memory blocks as they are allocated and freed. This does not actually include the allocations themselves. This only tracks the allocations. So this is going to incur a little bit of overhead when we go to set up an allocator for this, but this is only to manage the data behind that allocation. Most free lists use a linked list internally, and this one will be no different. However, this typically means dynamic allocations as we add and remove elements or nodes to the free list. And as you guys have probably gathered, we don't really want to do that. That's the reason we're writing our own allocators and things like that. So in our case, we won't be having these dynamic allocations, at least not once per node. We're going to allocate all the memory we need up front for the free list, and then go from there, okay? So what this means is we're going to have a single allocation, and we're going to pull from an internal array of already allocated nodes. And this is going to allow us to avoid dynamic allocation that's typically associated with linked lists, right? So what does a linked list look like? Well, it looks a little bit something like this. So we have various blocks of allocated memory and free memory, right? So these are all different allocations that have happened over time. And we have these free blocks of memory, which contain an offset, a size, and a pointer to the next free node. And what this does is the first node here points to the next available free block, which also has an offset and a size available, and it points to the next one and so on until it reaches the end of the list. And when we reach the end of that list, this next node will be null or 0. And that is how we know when we've reached the end of the list. So we have two different methods or allocation choices when it comes to how a free list is actually implemented. The first one is something that we call first fit, where basically it starts at the beginning of the free list and iterates through until it finds a block of memory that is big enough to actually hold the allocation, and then it uses that one. We also have something called best fit, which searches through all of the available free blocks of memory to find the one that is either an exact size or one that is the closest match possible. So first fit is generally quicker to allocate, especially when you have a lot of allocations, because it doesn't have to actually search the entire list. It stops at the first one that it finds. So this is good, but the potential drawback is it can lead to more memory fragmentation, because you'll have lots of little unused chunks of free memory throughout the free list, potentially, especially after a lot of allocations and frees happen, okay? And so there is a little bit smaller of a propensity to have memory fragmentation with the first fit model, okay? Best fit, on the other hand, is a little bit slower to allocate because it has to search the entire list for the best match. Now, arguably, if we find a block that is the exact size we need, we could probably stop at that point, and that would be an optimization that we could do there. But most allocations are not going to fit that criteria. So we always tend to look at the worst case scenario, which means that it has to search the entire list to find a block of memory. So this does mean that it's slower to allocate because it has to search that entire list. But it can also be slightly better at preventing memory fragmentation because it does try to find the closest fit possible. However, in most of my tests, this doesn't seem to be that much of a savings in terms of memory fragmentation. The benefits don't really outweigh the costs. And so we are going to be going with a first fit solution instead of the best fit, right? So what does an allocation look like? I know we've kind of touched on how that works a little bit, but what are the details of that? How does that actually work, right? So we have a block of requested memory here, and basically it jumps to the first, or the head of the list, right? The very first element here, and says, do I have enough free space? Well, if you can notice here, this block is actually a little bit larger than this free block here. So it is not actually going to be able to take this one. So it goes on and says, all right, this is too small. This one is also too small, right? But this one right here is actually larger than I requested, so it fits. So it's going to go ahead and allocate from this free node right here. And what this does is it shifts the beginning of the free node to after the size of the allocation and puts the allocation at the beginning of that node. And at that point, the offset of the allocation is returned. That's the offset from the beginning of the memory block, right? And then this free block is modified. And in this case, we don't actually have to modify any pointers, right? What does a free look like? Let's say we want to free this allocated block of memory here in this example, right? So this is all one allocation. It's not multiples like we see here. This is just one contiguous block of memory, and it is actually between two free blocks of memory. So we've requested a free of this block, which turns this block into a free block. That's all it really does, right? And that means that we also need to update a couple of pointers, because since this is now a free block, this free block here is now not the next one in line after this guy. So we need to change this first node to point to the second node here. And we need to change this second node to point to the previous second node, which is now the third node. And then from there, we're good to go. However, if we just stopped at this point, this could potentially raise a problem for us once we get further down the road, right? Because eventually these blocks are going to become smaller and smaller, right? And it doesn't really make sense for us to have three free blocks, one right after the other, right? So eventually we're going to wind up with not only crazy memory fragmentation, but we're also going to have a bunch of really tiny free blocks that aren't really usable for anything else, right? So we need to actually handle this scenario too. And what we actually need to do is we need to check, once we've completed the pointer updates, to see if there are free blocks on directly on either side of this. And we use the offset to determine that, right? And so in this case, we have two free blocks on either side of it. So we check one side first and say, okay, well, this block is right next to this one, so let's go ahead and combine those, okay? And then we go ahead and check the block on the other side and say, you know what? These guys are also next to each other, so let's go ahead and combine those. And that gives us one large free block, okay? So that begs the question, where will these be used, right? So one of the first places we're going to use this is our Vulkan buffer, because if you recall in our code, we've actually set our code up to use a sort of internal linear allocator that we don't ever free, and we just sort of keep moving this pointer or this offset along every single time we add to it, which obviously isn't going to work in the long run once we start to load a bunch of objects. So our Vulkan buffer is definitely going to need this, because we need a way to track those free blocks within that buffer. But we're also going to go ahead and set up a dynamic allocator for this, right? So what we're going to do in this video is we're going to review our free list and get that all set up. And then in subsequent videos, we are going to set up we're probably going to do the dynamic allocator first, and then we'll go ahead and set up the Vulkan buffer. And one of the reasons that I want to set up the dynamic allocator first is because there's a lot of places in our code that we are actually using kallocate, and we actually want to get away from that. We actually want to start using our dynamic allocator when we get to that point to perform our allocations. That way we don't have to reach out to the OS quite as much, okay? And so that is the general plan on how we are going to approach this. So today we're going to go ahead and look at the linked list. So let's go ahead and jump into that. Okay, so let me go ahead and blow this up a little bit so that you guys can see it. So what we're looking at right now is basically a diff between the temporary branch that I've created and the main branch. And this is in my sort of private repository that I use for staging changes and so forth. So what I'm going to do is go over the file lists that we're adding first, and then I will show the couple of files that we had to change. And then I'll jump into VS Code to actually go through the rest of this logic, okay? So the first file that we've added here is under containers, we've added a free list C and a free list H, all right? Again, we are going to be coming back to these things in just a second. So those are our free list implementation. We'll be going over that in a second. We've also added free list tests to our test project so that we can exercise this thing, make sure it works right. And so we've got a C file for that, and we've got a header file for that as well, which just contains our free list register tests. We also made a couple small changes to our tests main C, where we added a reference to our free list tests, and we register our free list tests, right? So that is basically the synopsis of the changes that we're going to be taking a look at, right? So with that said, let's go ahead and take a look at the free list. Now, you'll note here that I've got the entire header file already spec'd out. And you'll notice here that I've added a lot of documentation comments. I'm actually going to come back to that and touch on that at the end of this video, okay? But for now, let's go ahead and take a look at the implementation. So we have a structure type def here that only contains a void pointer to a memory block. This holds the internal state of the free list without the rest of the engine being concerned about what's actually contained in that. Because what's contained in that will vary depending on the actual free list creation itself, okay? And what I mean by that is here is our create method. So the create takes a total size, and that is the total size in bytes that the free list is going to be managing, right? So this would generally line up with the size of a Vulkan buffer or the size of a dynamic buffer. This would line up with that size. We also have something here, a pointer to a U64 to hold memory requirement. That is the memory requirement for this internal state, not to be confused with the amount of memory that this thing is going to be managing, okay? So there's two separate things going on there. The block of memory here, again, is for the internal state here. It is not for the memory that this is going to be managing. Remember, this free list does not actually manage memory itself. It is only a list of allocations, right? Or free blocks of memory, I should say. And then we have a pointer to hold our newly created free list. Okay, so this looks a lot like a lot of the other systems and things that we've created before. We're just sort of maintaining that same pattern here, okay? And so generally speaking, that means that you would call this twice because we need once to get the memory requirement and then the second time to actually pass through the allocated memory. And I'll explain why we actually need to do that in a second, because this actually will vary depending on the total size here, okay? We have our destroy. That's pretty self-explanatory, so I'll go ahead and skip over that. So we have here our free list allocate block. So this takes in a pointer to a list. It takes the size that we want to allocate, and then it also has a pointer to hold the offset of that allocation. So anything that, that calls this, at least for right now, should maintain a separate U32 offset, right? And we'll need to know that when we actually go to free the block of memory later, okay? All right, so the way that this works is you pass a pointer to the list, you pass the size that you want to allocate, and then you pass a pointer to a U32 to hold the allocation offset once it happens, okay? We also have our free, right? So this works as we discussed in the slides there. In this case, again, we take a pointer to the list, a size, and then we just pass the offset directly. We don't need a pointer because we're not going to be updating that this time. We just need it passed by value. And then we also have an option to clear the free list. That just takes a pointer to the list. Pretty self-explanatory. And then we also have a call here to obtain the free space left within the free list. And what this does is it basically iterates all of the free nodes and adds up their space together and then returns a U64 containing that space. Okay. So it's relatively simple in terms of interface and being able to use it. So at least for now, that is all the free list is actually going to do, right? So we'll go ahead and take a look at the implementation next, because the implementation, I think, is kind of interesting. So the way that this works is we have our internal state. So this is what this memory block holds, right? And one thing we hold is the total size, which is this guy here when we call create. That way we know how big in bytes the actual block of memory that this is going to be managing is. Okay, we have something here called max entries, and max entries is basically the maximum amount of free list nodes that you can have within this list, right? And that's solely based off of size, right? And we do a little calculation down here to figure that out. So I'll come back to that. I'll touch on that once we get into free list create. But that is basically the array size of this nodes array here, right? And so we have our nodes array here, which is a array of free list nodes, which we haven't touched on yet. But this is the array that we're going to pull from anytime we need to actually obtain a new node, right? And then we have a pointer to a head node, or the very first node in our internal linked list, right? So at least once you first stand up the free list, the head node is going to wind up being the only node that's going to occupy the entire block of memory. But it should always point to something, right? It should never ever be 0. So we've touched on these free list nodes. Here's the structure for that. And all this does is hold a offset size and a pointer to the potential next node if it exists here, as we've discussed before, right? So these things, I hope, should make plenty of sense. So moving on to our free list create, we calculate our memory requirement based on the size of the internal state plus the size of free list node times max entries. Well, how do we get this max entries? How do we figure out how many nodes we might need? Well, that is done by this calculation right here. So basically, we take the size of a void pointer, which is basically the size of any pointer, right? It's 8 bytes is the size of a pointer. And we take the total size and divide it by that, because this is technically the smallest allocation that we're going to allow. And this should give us a pretty good estimate of how many max entries we need, right? We just take total size, divide it by that, and that will give us the size of our array, and thus our memory requirement. And then we can also use that to figure out certain circumstances where this might not be optimal, okay? And that's what this block down here does. So what we're saying here is our memory minimum should be the size of an internal state plus the size of a free list node, and we're going to multiply that by 8 for 8 bytes. And basically, this is sort of the point that I figured out of there being diminishing returns, right? So if we have a linked list that is smaller than this amount, then that means that the internal storage or the internal state is actually larger than the data that we're going to be holding. And at that point, it really doesn't make sense to even be using a free list for this, right? So that generally means that it's going to be a really small block of memory that we're managing. And the overhead of this just doesn't really make sense for that, right? We might want to think of something more lightweight for that. And so I just go ahead and throw out a warning here saying that the free lists are very inefficient with amounts of memory less than whatever that calculated amount is. It is recommended not to use this structure in this case. So it's just a little bit of a warning to say, you know, hey, maybe don't use a free list for something that's a super small block of memory. All right, and then in our, so as we've seen lots of times before, we go ahead and assign our memory. We go ahead and zero it out. We set up our states and our nodes using our offsets. This is all stuff we've seen before, so I'm not really going to go into that too much. One thing that I will touch on, though, is the state head is actually set to the address of the first state node, right? And so that's actually where that takes place. And then we just zero out the offset, we zero out the next, and then we set the size to this total size of the array here, okay? And then the next thing that we do is we actually go through all of our state nodes, starting at 1, because we don't want to invalidate 0, right? Because 0 is our head. So we go through all of those and we set the offset and size to this invalid ID. We've used this for other things before, but this is a nice way to tell us whether or not a node has actually been used in this array, so that when we go to pick a new one out of there, we can say, well, look for one that's got an invalid ID, right? And so we go ahead and invalidate all the entries in that array except for the first one to accomplish that, okay? Free list destroy, all this basically does is zeroes out the memory and then sets the memory block to 0. This effectively makes it zeroed out so that the allocator or whatever provided the block of memory can reuse it safely, and it doesn't have garbage data in it, and it's zeros, okay? So our allocate block it's a little bit more code than what it actually does, but essentially what this does is we go ahead and grab a pointer to our state. We grab a pointer to the first node of the list, which is the head. And we also keep track of a pointer to the previous node, which starts off as 0. So every time we are moving forward through our internal linked list here, we're going to keep a pointer to the previous node. The reason we want to do that is if we take out a free list node, we need to actually update pointers. And in order to do that, we need a pointer to the previous node, okay? So we loop through all the nodes using a while loop in this case. And we basically say, well, if the node size is equal to the size, then we have an exact match, right? So this first if block checks for an exact match because this actually introduces a couple of edge cases that we need to consider. So the first thing that we're going to do is, since we have an exact match, that means that we're going to basically pluck that node right out of the list, right where it is, right? And this may or may not be the head node. We don't know yet, right? Because this could be anywhere within the loop. So what we do is we first set the offset to that node, right? The node's offset, rather, right? So we take a copy of that and assign it to our value pointed to by out offset. And then we create a pointer here to hold the node to be returned. And when I say returned, I don't mean returned out of the function. I mean returned to our internal array of nodes, okay? And so if we have a previous node, then we set the previous node's next pointer to the current node's next pointer, right? So basically just skips over the current node. And then we set node to return to node. If this node does not have a previous, the only way that can happen is if it is the head of the list. So in this case, the node to return is going to be the state head. The state head is going to be set to the node.next. Now, technically speaking, there could be issues with this if we allocate the entire thing in one shot. But generally speaking, we're not going to be doing that. So I don't think that's something that I really want to account for just yet. But you know, if we do need to come back and address that, I will. But I don't want to add the logic right now unless we actually have to do that. Okay, so it basically sets the state head to the node next, right? And like I said, this means that basically this is going to wind up being potentially set to null, right? If you happen to allocate the entire thing. So there could be an issue there. I do want to point that out. We probably will come back at a later time and add that to handle that if we need to, but for now, I'm not going to bother, right? Basically, if we have a null head, that means that the whole thing is full and we can't allocate, right? So what we do here is we go ahead and we call return node, which we passed the list and node to return. And we'll take a look at that in a second. And then we go ahead and return true, meaning that the allocation was successful. Otherwise, if the node size is greater than the size required, or the size that we're looking for, we go ahead and take the offset of that node. We subtract that size from the node size, and we move the node's offset by that size. So that's how we offset that, right? And then we go ahead and return true. Because we don't actually need to add or remove any nodes in this case. We just simply take out some of the existing node and return true. Okay, so if neither of these is true, then what that means is the current node that we've found is too small. And that means that we need to keep searching the list for something. So we go ahead and set the previous to node and then move node to equal to node next. Okay. And basically, if we get to the end of this while loop and we've not returned true, meaning we've not found anywhere that is capable of holding the allocation that we want, then we're going to go ahead and do a quick calculation on how much free space is available. Then we'll go ahead and warn about that, saying that we were not able to find a block with enough free space, and we'll indicate free space that's left here. We might enhance this later to run an algorithm to detect how much memory fragmentation there is. But for right now, I want to keep this simple, right? And then we're going to go ahead and return false, meaning that the allocation failed. Okay. So again, there's a couple of edge cases we haven't technically covered in here, but I think at least in this case, we shouldn't really hit those things right off the bat. If we do, we can come back and bug fix it later. All right, so the next thing is free block. Again, this does our standard checks. We go ahead and set up our pointers. We loop through just as we did before. So basically what we're doing is we're checking each node's offset to see if we find an exact match. And if we do, we're just going to add the size available to that node, and then go ahead and update pointers and return true, saying, hey, the free worked. This probably will very likely not happen. What we're going to wind up doing most of the time is this one, where our node offset is going to wind up being greater than the offset that we have, because we're going to wind up, generally speaking, iterating past where the actual allocated memory was, and we're going to wind up putting a node before that, right? And so we go ahead and we get a new node, and again, we'll cover this get node, but basically that just searches the array for a free node and pops it back to us as a pointer. And then we go ahead and set the offset and size of that node. And then we go ahead and update the pointers accordingly. So if there's a previous pointer, we go ahead and set the previous next to the new node, and the new node's next to the previous next node, right? Otherwise, the new node becomes the head, right? Because if there is no previous, then that means we're at the head of the list. So we set the new node next to node, and we set the state head to new node. We also want to double check the nodes on either side to see whether or not they are adjacent to our node, right? And so what we have here is we basically double check the next node to see if it can be joined, right? So it just does that by first making sure that a next node exists, and then checking the new node offset plus the new node size and seeing if that is equal to the new node next offset, right? If those two things are equal, then that means they're right next to each other. And so what we do then is we add the size of the next node to our new node. We take a pointer to our new node next, and then we set new node next to the next of that one, and then we return basically the old new node next to the array to be reused elsewhere. Okay. We do the same check in the opposite direction. So we just check the previous node. If previous node exists and its offset plus size equals our new node offset, then that means those two can be joined, and we do a similar thing here. Okay. Otherwise, we just keep moving through the list. If we reach all the way at the end and we say unable to find block freed, this could potentially point to memory corruption, or we didn't store the offset properly. So if this happens, we are going to bleat about it and return false. This should probably wind up being an error, but for now, I'm just going to treat it as a warning. Okay, so free list clear is actually pretty straightforward. So all it does is it basically starts at 1 and invalidates all the node entries once again, sets the offset of the head back to 0, it sets the size to this total size of the entire block that we're going to be allocating, and sets the next to 0, right? So basically just resets us back to our default. Our free space does exactly what I said it does before. It basically just loops through all the nodes, keeps a running total, adding the size as it goes, and then returns that running total, right? It's pretty straightforward. Our internal method here, so we have getNode. So this here iterates the state through all the nodes up to max entries and says, hey, if the offset is invalid ID, then this one's free to be used. Let's go ahead and return the address of that so that we have a pointer to a node to be used. Return node does almost the opposite of that. So it basically takes a pointer to the node that we're putting back, and it sets the offset and size to invalid ID so that it marks it as unused and then zeroes out the next. Okay, and that is the entire implementation of our free lists, right? So I know we did a little bit of a deep dive into this one, but because this is a little bit more algorithmic, as it were, I felt that it was a good idea to sort of really go into detail on how this works. Okay, so one other thing I really quickly want to touch on is I want to go over the testing scenarios. So I just added a few tests here, 5. So you guys can sort of review this on your own. I'll go through the first one probably, and then let you guys sort of review the rest of them from there. But we basically have, well, I won't go over this one. We have a create and destroy, right? That just makes sure that it sets up and tears down as expected. We have an allocate and free one, where it basically just makes one allocation and then frees it to make sure that everything is as expected. We actually, the naming of this one is a little bit wrong, but basically this one allocates and frees multiple entries, right? So we just do this same thing just multiple times. And then we do that again, but this time with varying sizes, just to kind of test that logic to make sure that, the logic to check the node not being big enough to allocate and move on to the next node actually works. So we just sort of exercise that code a little bit. And then we allocate the free list to full and then try to allocate one more just to make sure that the fail case for that works correctly. Okay. And so that is all there is to the tests. And most of these tests follow pretty much the same pattern. So here I'm actually creating a really small free list of a total size of 40 just to sort of test that our calculation works when we're checking to see the minimum size that we should be using with a free list and whether or not that warning is generated. So I put out a debug message here that says the following warning message is intentional because we know we're going to get one for that, right? The next thing we do is we allocate a block for the free list, and we call create again with that block of memory. And then we just verify that it was actually created. We verify the free space, and then we destroy and verify that things were actually zeroed out as we expect. Okay. We also pretty much follow those same steps everywhere. The only change really is where we check the free space. We do perform different size allocations, different frees in different orders, things like that. All these lists, all these tests actually call the same methods. And I put pretty thorough comments in here to go over what exactly is happening in the code so that you guys can review that, right? So I'm not going to do a deep dive on the testing scenarios. You guys are more than welcome to read through this code and, sort of see how that works on your own. Feel free to add tests. If there's a test you feel like I've missed, because I've only done 5 here, that should cover most of the scenarios. But if there's a test you feel like I've missed, feel free to let me know in the comments, and I can go ahead and get that added in. One test is to allocate the whole thing in one shot and then try and free it and then allocate again and see what happens. I'm pretty sure that'll fail. But, if there's anything other than that that you guys think of, please just leave it in the comments, and I'll go ahead and get it added. All right, so that is it for our free list implementation. So it's pretty straightforward stuff. One other thing that I did want to touch on, though, before we leave, is you'll notice, let me switch back views here. You will notice something that I did in the free list itself in the header file, is I went ahead and thoroughly documented all of our public properties and our functions and even the files themselves. And I've actually done this across the entire code base. On a separate branch here called doc, right? I've made a series of changes to the entire code base, right? At least the engine code base. So what I've done is I've gone through every file in the engine, and I've added a file header with a basic description of what the file actually contains. I've added a documentation comment on all of the public facing structures, and I'll get to public here in a second, as well as all of their properties. And I've also added documentation to all of the public functions. Now, when I say public, I mean things that are in the H files or the header files, right? Because most of what is in the C file is technically private to that file, so I didn't bother documenting most of that except where it actually makes sense, right? But for all of these public-facing things, meaning public meaning it could be used either in a different file or in a file that is outside the actual engine itself, I've gone ahead and added documentation comments. And this is going to allow me to auto-generate API documentation for the engine as we go. So it'll give you an extra way to sort of search and look up things, definitions of structures, parameters, search for things without necessarily having to refer back to the code file to do that. And you could do that in a browser. It's going to be web-based documentation that I'm going to be posting up on kohiengine.com. So what all these documentation comments mean is I've actually gone in here and configured a file for a program called Doxygen to auto-generate this documentation for us. So this is the configuration file for that. The details of this don't really matter, but what it means is that I can run a program called Doxygen, and it will generate a new docs folder here for me with HTML documentation inside of it. Right, so let me go ahead and open this with Chrome, right? And the nice thing about this is you can actually open this just locally, right? And you don't need a web server or anything like that to actually run this because it's just straight HTML. It doesn't have any sort of server backend. And so what's really nice about this is you have a listing of the files here, right? So you can drill down and look at a specific file. So let's say, for example, we wanted to look at, I don't know, application, right? It gives us a full breakdown of the application H file with a description, the includes that it uses. If you click on one of those, you can actually look at the file itself. And then as well as our type defs, right? And it gives us our documentation here, taken straight from the comments itself. And if we actually look down a little bit further, we get the details of that, where it gives you all of the parameters, what the return values are, standard things that you would expect to find in documentation, as well as documentation on which methods are deprecated or should be removed. Remember this get frame buffer size. This is something that eventually we're going to be replacing because we don't want to have to get it this way. So, you know, all of our individual files have actually been updated this way, right? So our defines.h has definitions for all the various types that we've put in here. So there's lots of documentation to look at. But if you wanted to look at Vulkan buffers, for example, you could type Vulkan buffer, right? And not only does it give you the structure in the file itself, but it also gives you all of the methods that are associated with that. So it gives you a nice searchable interface to be able to look this up. So you do have to have Doxygen installed in order to actually generate the documentation locally, as I've done. But you won't have to actually do that right off the bat, because by the time this video comes out, I will have published this to kohiengine.com and posted a link there to the documentation to be consumed by you guys. So this was just sort of a quick project update that I wanted to go ahead and notify you guys of. By the time this video comes out, this will already have actually been pushed. I probably am going to push the documentation changes to the code base today, as of today's recording anyway. And then, by the time you guys see this, it will have already been out for almost a week. So anyway, that is all I have for today. Thank you guys so much for watching. Toss the video a thumbs up. If you haven't already, consider subscribing. Go ahead and click the little bell notification icon there to get notified as to when videos in this or other series drops. And I will see you guys next time.